Let's get started.
Sure.
Chad Orzel, nice to meet you.
So
Virtually.
nice to meet you virtually. We did meet in person once.
We met in person. I was thinking about this actually. I knew it was an APS March meeting. I want to say Denver. It was a few years ago.
It was a few years ago.
Yeah.
I think it might have been Denver. That's one of the ones I was at. So
yeah. So it's one of the popular ones. Yeah. It seems to be only a few places that are willing to host a bunch of physicists.
So there's a legend that years ago, DAMOP, the atomic physics subdivision, had their meeting in Reno, and the legend is they were told never to come back because it was like 800 people who know math, and so didn't gamble at all. And
right.
The hotel lost a fortune on them. So.
Yeah, that makes sense. They probably should have had a bit of foresight.
Yeah.
So we're going to write a kid's book. Now, you've never written a kid's book, have you?
I have not. No, I've written a book where I talk to a dog, but
right. Yeah. One of my favorites. I was cleaning up the shelf, and I pulled your book off the shelf, and actually, since I purchased it, I have acquired a dog. When I first bought it, I didn't have a dog, so I'll try it out.
Try it out, see if it works,
and we'll see how it goes.
I get nasty. There are some comments and reviews every now and then I run across that are like, well, it's a really interesting book about physics, but like, it's not. It's like nothing about how to teach your dog. I'm like, what did you think you were getting?
I mean, I guess you could try. I mean, you could make some like parody videos where you get the treats out and you're like, if the dog can repeat something about tunneling, you throw it a treat.
Well, pirate copies of it show up with like in lists with like Cesar Millan books, but how to stop your dog from barking. So I figure those people deserve what they get.
Right. And I've read a couple of your other books since then. I don't know. So you also teach relativity to dogs, but I don't know which one came first.
The quantum one was first.
The quantum one was first. Okay.
Yeah.
And then you had Breakfast with Einstein, which I actually really enjoyed that one as well.
So, thank you.
And there was another one in there too. Am I forgetting?
It's, Eureka: Discovering Your Inner Scientist.
Yes, that's right. Yeah. And there's a new one that's going to come out. When's the date?
January 25th in the U.S. and like it's a week later in the U.K. I think.
Right.
February 3rd, something like that. So.
Yeah, I'll have to double check the Australian release date. Things due to the pandemic of I think supply chain has been disrupted quite a bit.
Yeah.
So it'd be a bit
everywhere.
It'd be a bit later potentially.
So.
But I'll put a link to the book where you'll see a blurb from me. So I got an advanced copy and I read it and I quite enjoyed it. And I would highly recommend it. So. Yeah. It's been something that I've been interested in thinking about foundations of physics. Obviously time is something that comes up. Mm-hmm. And when you start to think about it, you start to wonder, well, how do I know? How would I even know what this time is and how to measure it? So the book is A Brief History of Timekeeping, and these days publishers demand some wordy subtitle. So I'm sure there's a subtitle as well.
Yeah, it's The Science of Marking Time from Stonehenge to Atomic Clocks.
Right. Yes. So it's about the history of the way humans have kept time.
Yeah, pretty much the last 5,000 years of the science and technology that we've used to figure out what time it is and keep track of that as you go. So,
and it's certainly something
it's a longer history than people think. So.
Right. Yeah. Well, I guess my thoughts would be like, when you really think about it, you take time for granted, and it just seems so important to basically doing anything, especially if it involves other people.
Yes.
Yeah. And then you think, well, the ways that I keep time now are certainly weren't available
No.
5,000 years ago.
No, and it's a thing that people have been worrying about kind of almost as far back as we have evidence of people, right? I mean, the oldest arguable thing is there's, some tens of thousands of year old, it's like a chunk of antler that has little crescent shapes carved on it that some people think it's the phases of the moon. And so it's, somebody's like daily planner from 30,000 years ago, and people were keeping track of that stuff all the way back then. So
I feel like we're going to write timekeeping for babies, and I feel like this one, I don't know, it should be a bit easier because you can certainly point to objects around that keep time, even if the concept is a bit difficult. So when I think of if I was going to tell a child what time is, the first thing I would do is point to a clock. So what happens? What's happening inside of, let's say, like a wall clock, an analog clock? What's happening in there?
I would say actually you can go even simpler than that, which is to point at the sun. Right, and say, like, the simplest distinction and the earliest distinction that anybody makes in time is, day versus night, right? Is the sun up in the sky, or is the moon out, or, is it dark? And so that's really the very simplest thing. And so, and then you can tell, like, you can subdivide the day by where is the sun in the sky, right? As it rises in the east, it sets in the west. And you're looking at that, and where it is tells you, well, how much more of the day do we have before it sets, and you can subdivide things that way. You can do the same sort of thing with the moon and the stars. It's a little harder because the moon changes rapidly. Sometimes it's not up at all. The stars change position in a slow way, so it's not always the same stars that are right at the horizon when the sun sets. So it's a little trickier to keep accurate time by that. But, if you watch it carefully for a long time, you can see that. But really the simplest thing, if you want to introduce like a, really young child to time, the difference is it's daytime and it's nighttime. And that's really where it starts.
Right. That definitely makes sense. But I think that the way we interact with time, especially in these busy days, is more like, when a clock is showing a number, like, it's 8:00, we're late for school, right? I think there's something subtle in what you said that gets more to like the nature of time, right? That time is somehow just marking some repeating process, right? Day, night, day, night.
Exactly.
Yeah. Whereas we
you're doing that. Yeah, you're doing that in like it's very obvious in a mechanical clock. Like we've got a grandfather clock. I mean, not the full grandfather, but we've got a pendulum clock that we keep on the wall in our dining room. It used to be a relative of mine, and it keeps time with the swinging of a pendulum. So you've got a pendulum going back and forth. It makes the loud tick tock sound that characterizes a clock, and literally what it's doing is it's counting how many times has that pendulum swung back and forth, and that drives some gears that turn the hands on the clock. And then that's a really useful one with little kids because it chimes on the hour and the half hour. So it's very helpful to say, okay, yes, you're watching YouTube, when the clock bongs next, it's time to turn the turn YouTube off and go to bed. Right. And so that's a really really good impartial audible indicator of what time it is. That it's not just me saying that it's time to go to bed. It's no, that the bonging right, means it's time to go to bed.
Yeah.
So
the authority is the clock.
Yes.
Do you find so then? I don't. Yeah, that's interesting. So I wonder then in your house, do the children have a better sense of time and because there's this sort of thing that's sort of internally teaching them what a half hour an hour is?
I don't really know. They're still terrible at guessing durations of things. So like my 10-year-old will say like, yeah, well, this is going to take 5 minutes or an hour. And I'm like,
right.
Those are very different.
Right.
So, it's probably that's a range, and so maybe we could narrow that in a little more. So they doesn't have a great sense of how long anything is still. But.
So when this pendulum is going back and forth, I've always actually wondered this about pendulum clocks, because whenever I play with a pendulum, it gets damped almost immediately. It seems like a really bad way to keep time. So how do they continue to swing?
Right, so that's the genius of it is you have a gear, right, and you have the pendulum swings back and forth. And when it swings in one direction, it drops. You have this gear that's turning. You've got a weight or spring or something making it go. And when the pendulum swings in one direction, it drops a tooth in front of the gear and stops the gear for a second. And then that gear, right, pushes back on the pendulum and pushes it to swing in the opposite direction. So it gives the pendulum a little kick at the far end, starts it swinging back the other way with a little bit more energy than it would have if it just, came to a stop on its own, turned around and went back. And when it gets to the other side, it drops a tooth in on that side. Again, stops the gear, and again, the gear gives it a push and sends it swinging back the other way. And so it goes back and forth like that, stopping the gear periodically so you don't have the gear just keep, unspooling and unwind really fast. It regulates the way the gear turns. And it also keeps the pendulum going. So at every extreme, when it hits the gear, it gets a kick that keeps it going much longer than. So yeah, if you just take a ball and tie it to a string and set it swinging back and forth, you're lucky if you can get, it to go 20 times, let alone all day. But that kick from the gear keeps the pendulum and the pendulum clock swinging. So that's
So early clocks, maybe going back some number of years, would be accurate maybe only over the length of a day.
Yeah, the first thing that did wasn't actually a pendulum. It's called a virgin foliate, and it's like a heavy bar that twists back and forth like this. And then there's a vertical shaft that's doing the same thing. It's hitting the gear. And the bar twists back and forth, but that's really sensitive to two things. One, the exact shape of the bar and the distribution of the weight on it. So they're really hard to standardize. And the second thing is it depends on how hard you're pushing it. So, they would drive it by like hanging a weight, and that's what's making the gear turn is there's a spool with rope wrapped around it, connected to, this is like in a tower in a cathedral, right? And there's a weight that's falling slowly down the tower, pulling on the spool, driving it. If you increase that weight, then the clock ticks faster because it's pushing it harder and it's swinging it more violently. If you decrease the weight, it ticks slower. It also turns out if you wind the rope in a single layer on the spool, it goes at one rate. If you wind it, so there's multiple coils, it goes faster on the outer coils because you're putting a bigger torque on the gear that you're driving, and so then it ticks at different rates as it unwinds. So there's all these things that make it not work quite right. And so, like, those kind of clocks, the Virgin Foliot clocks, were accurate to, like, if you're really good, you could get it to like a couple of minutes a day. But like the very earliest ones, they didn't even have minute hands. They would just have hour hands because they were so bad. It was like 10, 15 minutes a day that they would drift by in one direction or the other. So you didn't even bother trying to keep time, finer divisions of time than the hours. And so,
Right.
so it's like, it's almost 300 years between the first mechanical clocks and pendulum clocks. And then pendulum clocks are very, very good because the pendulum is extremely regular and doesn't depend on, it's much less sensitive to the force that you're kicking it with to keep it going. And it's much better about, if you know the length of the pendulum, right, that sets the period of the swing. And it's much less sensitive to anything else. So pendulum clocks very quickly were accurate to, seconds per day. And then they're really useful devices for astronomy and things like that.
So most of the clocks I can imagine on people's wrists or on walls, they're all quartz now, right?
Yeah. So like high-end watches, this is my cheap watch. I didn't wear I have a fancy mechanical one. There are, and this is actually a weird inversion, right? You've gone for now. If you want to pay a lot of money for a watch, you're going to get one that's less good than the one you can get for $20 in Walmart, because the high-end ones are mechanical. And so they're still, it's a mass and a spring twisting back and forth that you use this to measure time. This one is a quartz watch, and so it's got a little quartz crystal in it that's shaped kind of like a tuning fork, and it vibrates very rapidly. And they cut these things so that they vibrate 32,768 times a second. Because that's 2 to the 15th power. And so you can just, you have something that's vibrating that fast, and you can divide the signal it gives you by 2, and then by 2 again, and then 2 again. And you do that 15 times, and you've got 1 per second. But the quartz crystal is extremely rigid. If you cut them the right way, they're not very sensitive to temperature. So they're, you precision machine those, and those are good to, seconds per month, kind of, if you have a really good high quality quartz clock. A cheap one is good to, like second every couple of days.
And cheap would be because the crystal wasn't cut the right way, and so it's not exactly this 2 to the 15 vibrations per second.
That, or it's not manufactured quite perfectly, so that it's a little more sensitive to temperature. They don't do, even the best ones are a little bit sensitive to temperature, but you can do things to compensate for that. You can add extra elements that control for, it ticks a little slower when it's really hot or whatever. And the cheap ones don't do that. They don't. Yeah, that adds complexity to the device. So the cheap one is just, here's a quartz crystal. It's going to, wiggle back and forth, and that'll be good enough for, And if you have to reset your watch, once a month or something because it's drifted a couple of minutes out, that's not that's not that big a deal. So.
Right. And then of course, I guess these devices, computers that people always carry around, they're never more than an inch from their body. They
Clock
keep,
right there.
Yeah, they keep so they must have like an internal ways to keep time, but also they're always syncing up with each other, right? So my time is probably very well synced with yours, I'm assuming.
Yeah, these are like the clock on a smartphone, right? Is there's some internal time keeping, I'm not sure with these. They may even include like a little quartz oscillator in there, because those are, super cheap these days. But if not, it's just an internal clock in the computer chips that maintains the time locally. But because it's a smartphone, it's constantly connected to the internet, and the internet, right? Every message that goes across the wires on the internet is time stamped, and that time is maintained very uniformly and synchronized across the entire world through the internet network. And so your phone will check in very regularly to make sure that it's keeping the right time. Same with like the clock on a desktop computer like the one I'm recording this on. You can go in the U.S. The National Institute of Standards and Technology, which is in charge of maintaining the official U.S. time, has a website you could go to and click a button and it'll tell you, the clock on your computer right now is, 60 microseconds off from the official U.S. time, and it does that. And some OS things, there's a button to like. Some versions of Windows and Mac OS, you've had the option to click a button and sync the clock to the official U.S. time, but it's never more than a fraction of a second off, because that network is constantly updating the time on all of the computers that are connected to it. Right.
It almost seems like a bit of a catch-22 if you think about it naively. That, I mean, you require all of the computers to be synchronized to maintain the way the protocols work, but at the same time, that's also how you keep the time. Like, can they drift off?
There's this really fascinating, and this is a process that happens a lot through the history of timekeeping, right? People start out keeping time by the sun, just what time of day is it, using like a sundial. And then, that has its limits because you need something that can keep time when it's cloudy. Like, happens a lot around here. It's raining right now here.
Same.
And at night, you can't tell what time it is using a sundial. So, people invented water clocks and mechanical clocks, and then figured out from that, hey, we can make these so they're really accurate, so they're really good and very reliable. And then you start to notice, once you've got one of these clocks that's really reliable, you start to notice that, wait, it seems like, the day is a little bit longer sometimes than you expect it to be, and it's a little bit shorter some other times. And you're like, okay, this is actually more reliable than my pendulum clock is actually more reliable than, looking at the position of the sun. And so people shift to, okay, now our definition of time is not going to be, where is the sun at a particular moment. It's going to be something involving one of these pendulum clocks that we know is extremely reliable and will always, let you keep track of the time. And then people changed over to the oscillations of light absorbed and emitted by cesium atoms, which is a similar idea. It's a wave that's going up and down, 9,192,631,770 times per second. I memorized this because I teach this a lot. And it's this 9.1 billion times per second oscillation, and that is guaranteed to be the same for every cesium atom in the universe. And so you can use that as your time standard, and so there's this sort of bootstrapping thing where we've got sundials, they're pretty good. Okay, now these mechanical clocks are better than the sundials, so we're going to shift, but we sort of tailor the mechanical clock so it matches what the sundial used to do. And now we got these mechanical clocks. Now these quartz clocks are better than the mechanical clocks, so we're going to fiddle with that again. And then you get the atomic clocks that are better than the quartz clocks, and you keep fiddling with your definitions so that all those digits, the 9,192,631,770, that is it's a weird number because that comes really, really close to the second as previously defined. And so, like that's what you're doing to match it. And, because if you were going to do it just from scratch, you'd say, let's call it 10 billion, right? And we'll have a second that's a little bit longer, but then the math is easy, right? And, but that's not what it's done. It's this strange number because we needed it to sync up with what we have from sundials and mechanical clocks and quartz clocks and all of that.
Right. Okay.
So it's a complicated process. So you were actually you started asking about network time, and that's one of these issues. Is you need the timestamps on the messages to synchronize the clocks, but you sort of need to have the clocks synchronized at the beginning to get the timestamps to begin with. And so there are these procedures for how you do that. You basically, everybody's got their local clock, and then you send signals from one to the other and then back. And that enables you to match up the clocks in different places so they all start out showing the same time. And once you've done that, then you can use them to do your network stuff. And then you're just making small tweaks. And they do, like, depending on backups in the local network and things, they'll get off by milliseconds or microseconds over the course of, it wanders. It's a little fast, it's a little slow as you go. The time will wander around a little bit, but it's never off by all that much. And so you just keep checking it very regularly. You get very accurate time. Right.
I think I have an idea for how I'll start sketching this, and so you'll see me looking down.
Okay.
And I was wondering, so if I want to think about time then as like repeated events, then the fastest number that is relevant to a human, I guess, is the definition of a second, or these 9 billion ticks per second. Is there's nothing faster than that is relevant to people? Is there?
I mean, so it's a question of what you mean by people, right? So if you mean like, in everyday terms, right, the fastest thing anybody actually cares about is a second or two. Or maybe, if you're like if you're a sprint racer, right, or a competitive swimmer, right, then maybe you need, hundredths of a second to time things. But normally the fastest thing that you deal with that you can perceive directly is kind of a second or a fraction of a second. Processes that matter, right, is, the 9 billion oscillations per second of the cesium clock transition. That's way too fast for anybody to really worry about. But there are, on kind of a biochemical level, there are things that are really incredibly fast that matter. So like your eye perceiving light, the light receptors in your retina, they register the absorption of a photon in something crazy short. It's like less than a picosecond that the chemical change happens that starts the cascade that triggers things. So there are these like absurdly fast events that are actually critical to building up what we experience as the world around us.
And what's the shortest sort of what's the right word? So what's the what is the longest period that we can imagine being relevant?
The longest periods that people imagine is sort of a lifespan, and so you think about a person, right? If you're lucky and you have good genes and good medical care and all that kind of thing, can live to 100 years, something like that. And so my great grandmother, when I was a kid, I remember going to her 90th birthday celebration, and that was in the early 80s. And she was born in 1890 something, and remembered a time before there were automobiles, right?
Right.
When she was a little girl, like, you wanted to go somewhere, you were going on either a train or a horse, because nobody had a car, and all of that came in. Telephones didn't exist, right? Like all the stuff that by the time she died in the 80s, right? There's commercial airplanes that going from New York City to San Francisco is like a 5-hour flight, and you're annoyed that it takes that long. Whereas when she was a kid, it was to go from where she lived to where we live in upstate New York, it's a 4-hour drive in a car. At that time, it would have been like a 2-day trip for her. So it's that's sort of the scale, the longest scale that people can conceive of, is sort of you get to be really old, you live kind of 80, 90, 100 years, you see amazing changes in the world, and that's sort of the longest span anybody can get their head around.
Right. Yeah.
It's an interesting thing that so like we in the West, sort of keep track of centuries, right? And that's kind of the big deal thing. One of the really cool calendar systems out there, there was a whole lot of buzz 10 years ago about the Mayan calendar, right? There was this idea that they predicted the world was going to end in 2012. They have this really intricate system of interlocking cycles. There's a set of 13 numbers and a set of 20 names, and those cycle through, and then there's another repeating set of things, and that defines kind of a system of 4 names that define a day, and those repeat on a cycle of it's like 52 years. So which again is kind of like, that's sort of a human lifespan, right? That's kind of the time between when you would be able to learn how the system works and appreciate that, okay, these dates are coming around, to like you're gonna maybe see the same set of 4 names come around. You might see it twice, right? You might remember two times it being this four name combination of figures, and that's, again, it kind of tells you something, that there's kind of a fundamental human scale to this. That's kind of that 50, 100 years is kind of the longest anybody thinks about.
So I'm sketching out the book here, and I trying to mash this all together in 10 pages.
In baby terms.
In baby terms.
Yeah.
So I want to get to like a point where there's sort of the aha moment, right? Where you say, I here's this device, say a clock, and you can recognize what it does because it's very familiar to you, and it's it's counting out. It's essentially just counting ticks, this periodic tick,
exactly.
tick, 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 and yeah. So where is there nothing more would you say to time than just how we keep it with ticking things, repeated things?
I would say from the standpoint of timekeeping, right, anything can be a clock, because a clock is just something that has a regular tick, right? So it can be, like literally the ticking of swinging pendulum driving teeth into gears, periodically. Or it can be, your vibrating little quartz thing, or it could be the oscillating light that comes from a cesium atom. So anything that does something regular. The other big historical ones are, and everybody's seen an hourglass, right? A sand timer. You have two balls with sand in them, and watch it drain from one to the other. Or a water clock, something you just fill a container with a fluid and let it drain out, and say, okay, each time this is empty, that we call that one tick, and then we can keep time that way. So from a technological standpoint, there really isn't anything more to it than the measurement. An interesting thing is, when you start talking about time more generally, like time in physics, you talk about it as sort of a dimension, but it's also, there's an element of sort of experience to it, that different people will see things happening at different rates. And so, and this is a thing that comes out of Einstein's theory of relativity, and also comes out of thinking about timekeeping. Because one of the ways you can derive the equations that lead to relativity is by thinking about this process where you synchronize clocks at two different positions by sending, you start with a signal here, you send it to another location, they send a signal back to the first place, and that exchange, that out and back exchange, allows you to synchronize the clocks. And that works beautifully as long as nobody's moving. Right, but if you introduce, and I kind of need a third hand to do it, but you introduce some other observer who's moving along, watching this process go by, they're going to say, no, that happened differently. The time that it took for the signal to go out and come back is not the time that you think it was. It's different than that because this person who's moving is totally entitled to imagine that they're standing still, and the two people who are synchronizing the clocks are moving. And if that's the case, one of them, in one direction, one of them is running away from the signal, and it's going to take longer. And the other direction, right, that person's running toward it, it's going to take a shorter time. And that means that the total time looks different from someone, if you watch two people doing this as they're moving, the time they think elapsed while they're synchronizing their clocks is not the time you think elapsed. And so people who are moving relative to one another end up having a different experience of time, right? The time runs at a different rate for someone who's moving relative to someone else.
Right. That was always the people like to say that quantum physics is strange and weird, but special relativity is weird enough.
Yeah, and then general relativity, right? And then it's even harder to explain. But if you bring gravity into it, then your position relative to a massive object changes the rate at which time runs. So if you have a clock on the ground and a clock at the top of a tall building, the clock at the top of the tall building is ticking at a slightly different rate than the clock on the ground. The clock on the ground is ticking a little bit slower, and you can actually measure this. And now some of these atomic clocks that people have are good enough that there's a group in Japan that did this with two clocks, one at the foot of the Tokyo sky tree and one at the top, and they can see the difference in the rate at which the clock at the top ticks compared to the clock at the bottom, and you can see that really clearly. And they're like 400 meters apart. There's experimental clocks in Boulder in the U.S. They did this where they raised one by 33 centimeters relative to the other, and that one, it takes a long time and you can just barely make it out. But you can see that there's a difference in the ticking of a clock that's a foot higher than another. Like two clocks that are identical atomic clocks, you jack one up by this much, and they tick at a different rate. And so where you are relative to the Earth determines how fast your clock ticks. So.
Yeah,
so it becomes
pretty wild.
something super complicated. Yeah.
Yeah. So is it the case
This
then?
is one of the. Yeah.
Is it the case then
Go
that
ahead.
the faster the tick, the more accurate it will be?
So the general way to think about it is if you've got something that ticks really fast, as long as you can count the ticks, right? Keeping time is ultimately I'm going to count how many ticks there were, right? And if you want to measure, say, 1 second, right, you want to know how many ticks were there in that 1 second. If your count is going to be kind of plus or minus one, right? Maybe there was a little bit extra at the beginning, or it came up just short at the end, something like that. Your uncertainty in how much time has elapsed is going to be plus or minus one of whatever tick you're using. So if in that case, then the faster the tick can be, the more accurate you are. Right. So if you've got something that ticks 10 times a second, right, then all right, I counted 10 of these, that's 1 second plus or minus a tenth of a second. Right. If it ticks 1,000,000 times a second, you count 1,000,000 ticks. Well, that's 1 second plus or minus 1/1,000,000th of a second. Right. And so the faster you can make your tick, the better you can know how much time has elapsed. And so that's why, that's one of the reasons why the cesium standard is this 9,192,000,000, right, ticks per second, because you want that number to be as big as you can get, on the theory that, if I can get this to within plus or minus one tick, then I'm going to have a more accurate read on what time it is. And these clocks that, the clocks that did the 1 foot difference, right, that measured the effect of gravity, those are using light at a much, much higher frequency. And so that's something like, that's like 1 quadrillion ticks per second for the light that they're using there. And if you can get that level of accuracy in your count, then then you're doing just an astonishingly good clock. And then you have to worry about things like, well, is my laser table level, right, or is one end of it higher than the other, when you start doing some of these experiments.
Right. Yeah. Or yeah. Or how the density of the Earth below you, or something like that.
Right. Are we over like a big gold deposit that makes the gravity a little stronger where we are than other places? There were one of the lab I worked in as a postdoc. One of the other projects, they had an interview with some Australian mining company that they had a method of measuring gravity, basically measuring, how much stronger is gravity here than here, right? It's just separated by some distance. And one of the things that'll tell you is there a massive deposit of something directly underneath you?
Sure.
And so they wanted to build this in a thing where they put it in a truck and drive it across the desert and look for fluctuations in the gradient of gravity that would say, hey, there's something really, really dense under this part of the desert right here. And then they go dig a big hole and see what it is. So is it gold? Is it or what? Buried alien spaceship, whatever. So.
Yeah, when you're looking for dense things, I think there's definitely a political joke in there for Australians, but I won't say it.
Yeah, it could be.
So I'm going to share the screen and show you what I've got so far. So let's see here. So you'll see the program, and I'm drawing this in, and all the books, they always start with "this is a ball." So the challenge is always how you're going to get from a ball to the topic. And I think the easiest thing is the shape. We'll play with the shape. So this is a ball, and I'll turn it into a clock. So it's really a clock. It has an hour hand, a minute hand, and a second hand. And then, I would redraw somehow the clock with the tick marks for the seconds. So we have one tick every second. A clock is just something that counts ticks. Anything that ticks is a clock. I don't like the word bad, but I couldn't think of a good short synonym. Some clocks are bad, some clocks are good, and some clocks are atomic. So, now you know timekeeping.
Nice. Yeah, that's good. Yeah, well, could you say you'd say some clocks are fast, some clocks are slow, some clocks are fast.
Right.
If you wanted to avoid bad and good.
Right. Right.
But I like that.
I like that. Slow. Fast. Yeah, okay. And I'll go back to Wikipedia for the exact number. 9,100,000,000.
It's 9,192,631,770. So,
do you know the next decimal place, or?
So it's defined to stop there. That's okay. Everything now, all of our units now are defined in terms of time and speed. The speed of light is 299,000. It's 299,792,458 meters per second. Full stop. It's defined to be that. And the definition of the second is defined to be exactly an integer number of oscillations of the cesium. And then the combination of those two gets you anything else you want, right? If you want to know length, right? Length is the distance that light travels in 299,792,458 of a second. And we use that definition for 1 meter. We use that as the definition of a meter because we have clocks that are so good. So because you can measure time incredibly well, then it's more useful to use your ability to make extremely precise measurements of time and the definition of the speed of light to define a length than it is to make an iridium bar and measure its length. The last one they just a year or two ago. They've now changed over. The last standard was the kilogram. They used to have like a physical, like weight, like shaped like your, the weights that you put on like a little balance. Mm-hmm. That was the definition of the kilogram, and they couldn't get away from that for a long, long time. But they finally did. There's now a chain of measurements, but what it amounts to is defining Planck's constant in terms of defining that exactly, which then connects time to energy, and you connect energy to mass through the speed of light. And so now everything is referenced to the speed of light and the definition of the second. And
right.
So even kilograms are now objects that are like if you're measuring a weight, it's ultimately traceable back to measuring a time. And so it's a cool quirk of how modern physics works, that we have this ability to measure time phenomenally well, and so we relate everything to that. And so
that's crazy. Everything is the cesium is the hero of the story.
and it's bizarre because cesium is super unpleasant stuff. It's like it looks kind of pretty if you have a chunk of it in like a glass vial. It's a pretty gold color. But it's a metal that It melts just below human body temperature. So we used to have vials of it for some experiment we were doing, and like if you just hold it in your hand for 10 seconds, it'll melt. And then you've got liquid. It just looks kind of pretty, but it explodes violently if it comes in contact with water, and just humid air will make it burst into flames. So
Okay.
so it's not, if you were going to pick an atom that you would like to have be the standard for things, you probably wouldn't go for that one because it's just so unpleasant to work with. But it turns out to be really useful for, and it has become the standard of time. So
it's interesting. I joked when I started making these videos that we'll make a baby book in 30 minutes. So this should have been the one that we actually tried to keep.
Put the countdown clock on.
But I reckon we had a good conversation. So I think we'll the bookmaking time definitely under 30 minutes. I'll call it. So thanks a lot for doing this. As I said, for those that enjoyed this, there's an adult version. We'll put the link in the description. Brief history of timekeeping. He's got excellent, the cover. Yeah. Definitely recommend that one. And maybe I'll improve the sketches on this one, and we'll throw that one out there.
So that'd be great.
All right.
This was fun. Thanks for inviting me.
Yeah. See ya.